So remember we started 4.3 and 4.4 on Friday. So quick reminder, we're talking about global maxes and global mins. And if I say absolute, it means the same thing. I caught myself saying absolute a lot in my last class. So absolute max min, global max min, same thing. So remember, we kind of have three different situations we can be in. We can either be on a, what's it called? A closed interval, an open interval, or the entire real line. Now you could also be on like part of the real line. Say one of your endpoints would end up being an infinity or a negative infinity. We also have to use the real line case in those situations too. But so remember, essentially what we're looking for is the highest point and the lowest point on a graph, the absolute highest and the absolute lowest. So that's where we're at. I felt like there was something else I was going to say. Oh yeah, remember specifically in that real line case, there's like two different processes. One of them, we find all the critical points and then plug in the endpoints and the critical points and find the largest value or smallest. But then remember with the real line case, that's where we still need to do kind of that first derivative number line to figure out what the graph looks like. So we finished with this one the other day and we did it in a bunch of different ways. And I, right before class, just realized that I never posted the notes to Blackboard, which I swore on my life I did. I forgot to upload the lecture. That was my bad. But I really swore that I had uploaded the notes and I didn't. So those will be up today with the rest of them that we do today. So sorry about that. No one told me they were missing, but I mean, it's still my fault. Anyway, so we finished on that one. And so today what we're going to do is we're going to talk about a lot more contextual based ones, as opposed to this one, which was kind of just here's a generic function, find its global max or mins, and we're going to go into a bit more context. Now with the contextual ones, this one that we finished on the other day, it's really nice because it just states the interval for you. On some of these contextual ones, they don't tell you kind of that clearly. Sometimes they do, but a lot of times you'll have to find the interval yourself using the context of the problem and the types of variables that you're looking at. So let's start with this one. Also, what we're going to find today, sometimes we're going to have two equations and we're going to kind of have to manipulate one and use it in the other equation. You'll see what I mean in a second, probably, hopefully. So let's say we have the product of two numbers is 20, and we want to find the minimum sum of one of the numbers plus 5 times the other. So I essentially get two different equations from that statement. The product of two positive numbers is 20, so we would get like x times y is 20, so I'll take those to be my two positive numbers, x and y. And then we're told that the sum of one of them plus 5 times the other. So we have like x plus 5y. Now it doesn't matter if you had written 5x plus y. It's just that, you know, your answers would quote unquote switch. Like my x value would be your y value. But it doesn't really matter because it's just the name of the variable. So you could have technically written 5x plus y. It doesn't really matter. Yeah, I can reshare. And yeah, the lag seems to be really bad today. So I'll try to focus on mine and see if I can, well, that's all I can do is go as fast as mine allows me to go. But if yours is lagging more than mine, let me know. So essentially, this sum is what we want to minimize. We're asked to find the minimum sum. So we want to minimize this equation, but notice that on the left, so I know that s is a variable too, but on the left side of that equation, there's two variables. And we don't actually know how to find the derivative of a thing that has two variables in it. We only know how to take the derivative when it only has one variable on each side. So we actually can't do this yet. But that's why we have essentially this other equation popping into our lives, because we're going to be able to use that second equation to replace one of our variables in the one we actually want to minimize. So we essentially need to get rid of either x or y. Since the x is by itself, I'm going to get rid of that one. You could get rid of whichever one you want. It's just that the algebra can get a little grosser depending on which one you choose. But since the x is by itself, I'm going to shoot to get rid of that x value. So what I would want to do is I would want to take this equation x times y equals 20, and I would want to solve it for x because I want to replace that x in the other equation. So we would get 20 over y. which is also 20y to the negative first. So I'm going to take that x value and I'm going to rewrite, I'm essentially going to replace what I just found that to be equal to in my second equation. So, one second. So now we've replaced that x value with a y. So now that there's only one variable type on the left here, we can actually take the derivative. So since we want to minimize something, remember, whenever you want to maximize or minimize, whether you're talking about local or global in general, the first thing you always need is the critical points. So we'll need to find the derivative and set it equal to 0. So we need to find the derivative, so s prime. So the derivative of 20y to the negative first, that's a power rule. Bring the power down, you'll get negative 20. Subtract 1 from the power, you'll get negative 2. And the derivative of 5y is 5. Now, technically, remember that this will be equal to 20 over y squared plus 5 equals s prime. So one thing really quick, talk about undefined. Well, we have a denominator here. It's y squared, so we have to set that equal to 0. So that'll give us y equals 0. But in the very beginning of the question, it says the product of two positive numbers. Y is not, 0 is not considered to be a positive or a negative number, really. So we just don't care about it. So we're going to take that out of the running because 0 isn't really considered to be positive or negative. So what we need to do then is we need to set the derivative equal to 0. Let me try to make sure I have enough space to write the answer. So I'm going to add that 20 over y squared over to the other side. You could keep it as 20y to the negative second, but at this point, I think it's easier to see what's next in the algebraic step if you have it as a denominator. Because what we want to do now is we want to multiply both sides by that y squared. So we'll get 5y squared equals 20, divide both sides by 5. Square root both sides. In general, you get plus or minus 2. But we're only taking positive numbers, so we'll just care about the positive 2 and not the negative 2. Now, wait a couple seconds in case people are catching up. So at this point, to be able to move forward, we need to know what type of interval we're working over. Do we have a closed interval, an open interval, or are we working over some portion of the real line? Are we going to an infinity or a negative infinity? Was that? Sorry, I thought I just heard a noise. Let me come back over to the very left side really quick so that I can leave that right side for my answer. So we need to kind of consider what interval we're working over. So we have y values here, so let me put y and I'll put the interval that we're working over. What's the smallest y could be? Well, the smallest y could be is essentially obnoxiously close to 0. We're not going to be able to be 0 because, again, 0 isn't really considered to be a positive number, but I could be as close to 0 as I want. So I'm going to say that the end of my interval is going to be 0, but with an open parenthesis instead of a closed bracket because I don't want to be equal to 0. And then what's the largest y could be? Well, we're just talking about positive numbers. We're not really given a stopping point. So I could make this as large as I want. So I could go all the way to infinity. So essentially what we now have is we essentially have to use that real line situation because of the fact that we have this infinity. So we're essentially in the real line. What's the word I want? What's the word I want? Real line, I'm going to say situation. That's not the word I want, but it'll work. I think someone just popped in unmuted. Or maybe I'm just going insane. That's very possible. No, everyone's waiting. Yeah, okay, I'm insane. So we're on a real line situation, so that's where we essentially need to use the first derivative number line. Now, we have a critical point at 2, and I'm going to kind of put this kind of here to tell me that I have to stop at 0 because I'm not going anywhere behind 0, not using any negative numbers. But we need to see what the shape of the graph looks like here. Remember, that's kind of the point of using this number line for these. So we pick our test points. We plug them into the derivative. Let me remind us where the derivative is. So if I put 1, we're going to get negative 20 over 1 squared. So negative 20 plus 5 will give us a negative. And then if we plug in 3, we'll essentially get negative 20 over 9, which comes out to something less than 5. I don't know what the actual number is. You can punch it into a calculator if you don't believe me, but we'll get a positive number. So essentially we have that the graph takes this kind of shape. It decreases and then increases. Come on, screen, catch up with me. Please, thank you. So remember, the point is to kind of look at what happens at the end. So essentially it's going upwards on the left forever and upwards on the right forever. Now I know it technically stops at 0, but remember we kind of have that weird situation with open intervals where it never actually reaches 0, so it kind of does go up forever in a way. So, but essentially the point is, since it goes upwards in both directions, we know that there is going to be a minimum. So remember, that's kind of the point of this, is we need to check the shape of the graph to make sure that the global max or min, depending on which one we want, can actually exist. But since a global min can actually exist here, it is going to exist at this local min. So we're going to have a global min at y equals 2. And then we need to figure out what x is. Now I'm going to tell you what it is, and then I'll tell you how I found it in case you don't realize. Let me use another color here. So x equals 10, I'm essentially coming back to this idea that x equals 20 over y. So from the kind of very front of this question, if you will, we found that x equals 20 over y. So if x equals 20 over 2, then that's where I'm getting the 10 from. Now with these contextual ones, you always want to go back at the very end and reread the question and then make sure that you have actually answered what they asked of you. So they ask us find the minimum sum of one of the numbers plus 5 times the other. So they actually want to know the sum. So now that we know x and y, we can actually find the sum. So the sum would be our x value of 10 plus 5 times our y value. So the sum that they actually care about is going to be 20. So that's the minimum sum in that situation where we have two numbers that are multiplied together to get 20, and we take the sum to be one of the numbers plus 5 times the second. So just a quick run through of what we did. We had this question, it gave us two different equations. The one of them we wanted to minimize, but it had too many variables in it. So we went back to the other equation, rewrote it to be able to replace one of the variables in the thing we actually wanted to minimize. Once we had the one we wanted to minimize in just terms of one equation, we could find the derivative, set it equal to 0, talk about undefined if we need to, and then we take that critical point, and since we're in a situation where one of our endpoints was going to be infinity, we need to look at a number line. We looked at the number line, we saw that global mins can actually exist, so it must have been at questions, concerns before we do another one. Okay, wait like 5 more seconds just in case people are still catching up, and then we'll go on to the next one. All right, so the next one's pretty popular. I'm pretty sure you see one of these in your homework. I think you see one of the ones we just did in your homework too, but anyway. So say we have 800 feet of fencing to fence off some land that has a river on one side. What is the largest area I can fence off? So first thing, let me try to draw what we're looking at here. That's a river. So we're essentially fencing off a piece of land by a river, but we don't need to fence off the side that has the river. Say we're just like keeping some cows in there, and we're pretty sure the cows aren't going to go swimming in the river. Maybe they will. I don't know. Anyway, we don't need to fence off the side that has the river on it. Let me give these some values. So let me name those two X and that one Y. So now we need to kind of figure out what functions we're working with here. So I want to know the largest area. So I'm going to move that over here. I'm strategically moving it over there a little bit because I want to write something else on the left. So essentially this, oh my goodness, this is what we want to maximize. And I'm getting that just from geometry. Area of a rectangle is X times Y. Well, in this case, length times width. Now the other thing is, so I want to maximize this, which would mean that I would want to take the derivative of that. But again, it has two variables in it, and I can't take the derivative of something that has more than one variable in it. Different types of variables. So I have an X and a Y, and I can't deal with that. But I'm also told that I have 800 feet of fencing. And let's assume that I'm going to use all of this fencing. I'm going to use all 800 feet. So if we think about that, we have two sides that are X and one side that's Y. So if we take essentially the perimeter of what we're fencing, that would have to be equal to 800. If we're assuming we're using all of this fencing. If we want to maximize area, we should probably use as much as we can. So essentially now I have the function I want to maximize and a function that I'm going to be able to manipulate to replace one of the variables in the area equation. So I want to solve this 2x plus y equals 800 for either x or y. I would personally solve for y because it's just going to be one step instead of two. But I mean, whatever floats your boat. But I don't want to have to divide by that 2, so I'm just going to solve for y. So subtract 2x from both sides. Catch up with me, screen. Again, some of your screens might be caught up, but just in case some aren't, I'm going to wait until my screen catches up. And choke on my water, apparently. Okay, sorry about that. You know it's a bad day when you can't even drink right. All right, so we've just solved for y. So we essentially want to replace that in our area equation. So we'll get x times 800 minus 2x. So now that I've replaced that variable, I'm going to be able to take the derivative because I only have one variable now. 1 second. Okay, but to be able to take this derivative, I would have to use a product rule as it stands right now. But if I distribute that x, I won't have to, so let's go ahead and do that. So we get 800x minus 2x squared. So now I have the thing that I want to maximize, only in terms of one variable on each side. So I can take the derivative. Before I do that, I want to come back and I want to find my interval that I'm working over really quick. Let's do that. So let me come back over here onto the left side just so that I don't run out of space. And let's kind of think about what interval we're working on before we go about finding the derivative. So this one is a, no, not even going to say that. I'm just going to start talking. So what's the smallest x value you could have here? Now, it might seem silly to say so, but you could essentially have something really close to 0. I know it wouldn't make a lot of sense if you like are trying to keep cows in there, but say you're just trying to fence this off for giggles, then you could have like each side x be 1/2 and then just have a really small like strip of land that's fenced off. It seems really stupid, but you could do it. And then what if you went to 1/4 or 1/8 of an inch or 1/16 or whatever? So we could essentially get x as close to 0 as we want. So let's go ahead and say the smallest value we can be is 0, but not 0. So I'm going to put an open parenthesis. I'm going to say that we're not allowing it to be 0 because we actually need, you know, an area. if one of the sides is 0, then you just have a straight line of fence, and that's not what we want. We actually want an area. So even if the one side is obnoxiously small, you do technically have some kind of fenced off area. Anyway, now thinking about the largest x value here takes a little bit more thought. And it has to do with this 2x plus y equals 800 equation. So there's two ways to think about it. You could think about it and literally just ask yourself what's the largest x could be. But I think it's actually easier to think about it as when x is smallest, sorry, x is going to be largest when y is smallest. Like the smaller that y side is, the longer the side x is going to be. So what's the smallest y could be? Well, y could essentially be quote unquote 0 as well, right? So if y is essentially 0, then we're going to have x be as large as possible. Now the thing is that we have two sides that are x's. So if y is essentially 0, we still need to break up that 800 that we're essentially left with into two pieces. So the largest x could be is actually just 400. But again, I'm going to put an open parenthesis there instead of a bracket, because again, saying that it's equal to 400 would make y actually equal to 0, which again wouldn't actually give us an area of fencing. It would just give us a straight line of fence. But that largest value came from essentially saying, well, y could be pretty much 0. And if y is pretty much 0, x is going to have to end up being essentially 400. And again, it's 400 because it's got the two pieces instead of just one. Anyway, so I'll wait a couple seconds in case someone's typing a question about that. But now that we have our interval that we're working over and our equation, we can maximize it. Sorry, I'm still haven't recovered from choking on my water. So we have an open interval here, so we're not going to need to do that number line stuff, which is cool. But we do still need to find the derivative, set it equal to 0. So let's do that. So find the derivative, 800 minus 4x. Let me just say not never undefined, so we know that we talked about it real quick, but there's no denominators there, so we don't have anything to consider for undefined. So now we want to set it equal to 0. Add 4x to both sides, divide by 4, you get 200. So now remember, with an open interval, we essentially do the same thing as we do with a closed interval, except the endpoints can't win. Remember, that's not like the official way to think about it, but that's the way I like to phrase it, is that the global maxes and mins couldn't actually be at an endpoint if that's what they were going to be. But remember, we essentially take those endpoints. I'm going to space this out specifically. So we take those endpoints and the critical points, and we're going to plug them both into the function, the area function. And remember, when you're plugging them in, you need to plug them into the original thing. Now, I should be careful with original in this context because there's like 5 million different original equations. I need to plug it into the original area equation, but I can take any form of the area equation I want. So I could use the x times y. I would have to find y in each case. But I could also use that 800x minus 2x squared, which is what I would suggest doing instead of having to find 0 in all those cases. So if we find the area in all of these cases, so if we plug in 0 to the area equation, we get essentially 0 minus 0. So we get 0. If we plug in 200, so 800 times 200 minus 2 times 200 squared, you'll get 80,000. And then if we plug in 400, we'll also get 0 again. I went through those kind of quickly because I trust to believe you could plug them into a calculator. So remember, at this point, you just pick the lowest or largest value depending on what you want. Since we want the maximum area, we'll pick the largest value, which hopefully pretty obviously is that 80,000. So also one last thing I'll say really quick before we write the final answer. So in this case, say we were asked for the minimum area for some strange reason. If we wanted the minimum area, it would have been essentially a tie between x equals 0 and x equals 400. But since those are endpoints and our endpoints are open, there wouldn't have been a global min then. So we would say there is no minimum area. But since we weren't looking for a minimum area, we don't care. But just in case, making sure that's clear. In this case, since it's an open interval, those endpoints couldn't win, as I like to say. But anyway, so what are we actually asked for? We're asked what is the largest area. So we want to tell them the largest area. So the largest area is 80,000 feet squared. I'm going to put down both the other values as well. They don't specifically ask for them, but I'm just going to write both down. So with x equals 200 feet and y would be equal to 400 feet, I believe. And just in case, where the heck did I get that from? This is when I go back to that y equals 800 minus 2x. 800 minus 2 times 200 gives us 400. So that's where I'm getting the y equals 400 from. So one thing with these contextual problems, again, go back at the very end, triple check what are they actually asking you to state. But it is also a good idea to just find both of the values if you have more than one value. Your questions on Wiley will usually want both, I believe, if I'm remembering correctly. So remember that you can always take that one value, go back to kind of one of your original things from the original problem, the beginning of the problem, I should say, where you found that the other variable was equal to something, and then use that equation to find the other value. Questions, concerns on that before we do another one? We have 2 more. You might be able to do both of them. All right. I'm not seeing any questions, so we'll move on. Okay. Scroll, please. Scroll. There we go. So one important question that a company could ask would be, when is profit maximized? That's pretty much what everyone wants to try to do, right? Make the most money. So we could use the techniques that we've been talking about in this section. But if you think about what that means, so we've been finding, whatever function we want to maximize or minimize, and then we find the derivative and set it equal to 0. So if we were talking about profit, we want to find when marginal profit equals 0. But also there's another thing we can think about when it comes to profit, because remember that marginal profit is made up of marginal revenue minus marginal cost. That cube looks ridiculous. So essentially, setting marginal profit equal to 0 would be equivalent to setting marginal revenue equal to marginal cost. So that's like a different way we could focus on these profit ones. And it kind of depends on what you're given. Sometimes you're given the profit function, so then just find the derivative and set it equal to 0. But like this next example, we're given revenue and cost. And sure, yeah, it'd be easy enough to just find the revenue function. But sometimes you can, I can formulate questions where I don't actually give you the function and I just give you the marginal values or something like that. So we do want to keep in mind that you can also find the same points where marginal profit would be equal to 0 by setting marginal revenue equal to marginal cost. So that essentially is finding our critical points for us. But anyway. So let me try to keep that in there a little bit. There we go. So we want to look at this one where it says find the quantity which maximizes profit if the total revenue and cost in dollars are given by those 2 equations, where Q is quantity and we're restricting ourselves between 0 and 1,000 units. what production level gives the maximum profit. So this one, unlike the last two, well, I was going to say we only have one function to deal with. Shall I say we only have functions in terms of one variable, so we don't have to do any of that kind of solving one equation and replacing it in the other. So since we only have one variable that we're working with here, and that variable is Q. So we essentially want to maximize profit. So, we would want to set marginal profit equal to 0, which we could find the profit function, or as we just saw, we could just set marginal revenue equal to marginal cost. So let's go ahead and do it that way for this specific question. First thing I would need, though, is the actual marginal revenue and marginal cost equations. So let's find the derivative of both of those equations once this screen catches up to me. There we go. So let's find the derivative of both of those. So the derivative of revenue would be 5 minus 0.006Q. And the derivative of cost would just be 1.1. Let me kind of break this up a little bit so I don't run out of space. So we can find the critical points that we need by setting those two equations equal to each other. Because remember, to maximize something, we do need critical points, but we just found that this is another way to find the critical points of the profit function. So if we subtract 5 from both sides, we'll get negative 3.9 equals negative 0.006Q. And actually, this turns into a pretty nice number when you divide both sides by the negative 0.006. You get 650. So now we need to consider what type of interval we're over. Well, we're given an interval of 0 to 1,000, and it's a closed interval. So that's really nice. We don't have to do that number line again. We just go ahead and plug in all of our endpoints and our critical points, pick the highest number and the lowest number. So let's go ahead and do that. So, well, we do need to be slightly careful here because we're going to need to know what profit is at all of those points. But we can just do our revenue minus cost then. Again, we still don't need to actually find the equation. So say we'll have Q equals 0, we'll have Q equals 650, and we'll have Q equals 1,000. So if we consider all of these, so we'll need revenue of 0 minus cost of 0. I'll take a breather for a second. If we plug in 0 to revenue, 5 times 0 minus 0.003 times 0 squared, we essentially get 0. If I plug in 0 to cost, we're going to get 300 plus 1.1 times 0, so 300. So we'll get negative 300 as our profit for 0. Revenue at 650 minus cost at 650, 650. I'll trust and believe my notes here. 1982.5 minus 1015.
There you go.
What?
And then we'll get 967.5. And then if we plug in 1,000. Let me try to, there we go. If we plug in 1,000, we should get 2,000 minus 1,400, which would give us 600. So here we want the maximum revenue profit, sorry. So what's our largest number? It's that 967.50 cents. Just to go a tiny step further, if we had wanted the minimum profit, it would of course be that negative 300. But we don't care about the minimum profit, but I just wanted to state it really quick. So we know that the maximum profit is this 967.50, but what are we actually asked for? What production level gives the maximum profit? So what they actually want is the Q value. So we have maximum profit at Q equals 650. That's enough to answer the question, but I'm going to go the tiny step further and say for a max profit of $967.50. Questions, concerns there? I'll wait a couple seconds in case people are catching up. And then we should have time to do the last one, which is nice. All right. No questions? Okay. So the last one has a bit more work in the beginning before we actually do a max or a min. And this is kind of going back a little bit. It's a little bit of like flashback question type of deal. So we have at a price of $80 for a half-day trip. A whitewater rafting company attracts 300 customers. Every $5 decrease in price attracts an additional 30 customers. So we want to find the demand equation, express revenue as a function of price, and then essentially maximize revenue. Now, because eventually I want revenue as a function of price, so R equals F of P, let me go ahead and find demand as a function of price as well. So with demand, remember, you kind of get to choose if they don't tell you which way to do it. But since they're going to want revenue as a function of price, let's go ahead and make our lives a tiny bit easier and also do demand as a function of price so that we don't have to then change it over before we find revenue. So let me split this up a little bit. So to find demand, we're going to want some Q equals MP plus B. I should have said assume it's linear. Assume demand is linear. I should have said that, and I didn't. Sorry. But we're going to assume it's linear, so we're going to assume it's some MP plus B. So the information we're given is we're essentially told that $80 gets us 300 people. So a price of 80 is attached to 300 people. And then that second sentence is actually essentially setting up our slope for us. So if we think about the slope here, that would be a change in Q over a change in P. You know, change in quote unquote Y over change in quote unquote X. So the change in Q, well, that's going to actually be the amount of customers. Well, we're told that it attracts an additional 30 customers. So we would have 30 over, and then the change in price. Well, it tells us for every $5 decrease. So the change in price would be -5. So our slope here is going to end up being -6. Because again, that second sentence essentially sets up the slope for us. It tells us that a decrease in $5 attracts an additional 30 people. So with the slope and that point, we're able to find the equation of the line because we can plug in those numbers and then solve for B. So we have 300 equals -6 times 80 plus B. So, whoops, 300 equals -480 plus B. So B is 780. So essentially that means that our demand function is Q equals -6P plus 780. And then our revenue. So remember, revenue, and I put that P there because it's being a function of price, is price times quantity. We learned that way back when. So essentially we're going to take that Q value and replace it with what we just found demand to be. And then to make the next step easier, because if we want to, whoops, if we want to maximize this, we're going to want to take a derivative. If I don't push through that P, if I don't distribute it, then we're going to have to take a product rule. And if we distribute it through, then it just turns into some power rules. So if we distribute that P, it kind of makes the derivative easier to find because it makes the rules simpler. But we've essentially done those first two parts. We found the demand equation. We've expressed the revenue as a function of price. So now we want to know what price the company should charge to maximize revenue. So we essentially want to maximize this negative 6p squared plus 780p. So we've got revenue. Let me just rewrite that. But also, before we go forward, let's talk about what interval we're looking over to figure out what type of situation we're in. Again, situation is not the word I want, but anyway. So what's the smallest price could be? Well, technically, they could let it be free. So we're going to say that it could be equal to 0. If you want to get sassy, you could probably say that they could be negative, but then they would be giving people money to, water raft, which would not make much sense. It doesn't make a lot of sense business-wise to make it free either, but they could. But then if you think about what's the largest P could be, it could technically go on forever. You could make it an obnoxious amount of money. You probably won't have many people coming to your whitewater rafting thing, but you could make it obnoxiously expensive. So essentially, since one of our endpoints ends up being an infinity, we're going to have to use that number chart, which is kind of the unfortunate case, but it's what we're in. So as always, for any max-min problem, we always start with finding the derivative, setting it equal to 0. So let's find the derivative. Negative 12p plus 780. And we want to set it equal to 0. It's also never undefined. So let's just make note of that. There's no denominators there. So we set that equal to 0. I should have added the 12 over to the other side. Oh well, same idea. So we do some algebra. We will get that P equals 65. Now, we need to check with a number line. Now, I know with these contextual ones, it almost seems silly because pretty much the answer is always at the critical point. But you always have to check because I could write some kind of trick question where there actually isn't a maximum revenue. And if you didn't use the number line to check how this, the shape of the graph is, you wouldn't know that. But so we have 65 on here, and then I'm going to also block it off at 0 because, again, I want to know that I'm not going past 0. I'm not using any negative numbers. So I need to choose some test points. So I don't know, I can choose 1, and I don't know, let's go with 100. Why not? And we're talking about the derivative of revenue, so I have to plug them into the derivative. So if I plug in 1, we'll get negative 12 plus 780, which will be a positive number. And then if I plug in 100, negative 1,200, negative 1,200 plus 780 will be a negative number. Plug them into your calculator if you need. So we have that the function is increasing and then decreasing. So essentially at both ends, it's going down forever. Now I know there's technically that endpoint of 0, but we're talking about a maximum. So that 0 is not going to be the maximum because we have this local max at 65. So since we have that local max, it's not going to be down at 0. So we consider 0 in this case, quote unquote consider, because that endpoint is included. I didn't really talk about it in one of the other ones we did because the 0 had a parenthesis on it, so it was open. But since this is a closed bracket, I'll talk about it for those 2 seconds, but it won't be the global max because we have this maximum value at 65. Anyway, so we'll have a global max at P equals 65. So let's go back to the question and see what it's asking for us. What price should the company charge per trip to maximize revenue? So essentially we've already answered it, but let me just phrase it in a bit more word-wise instead of P equals 65. So max revenue occurs when the price is $65. We didn't really need to know the max revenue. They didn't ask for that. We could find it if we wanted to. We would take that 65 and plug it back into the original revenue function. I'm out of space, so I'm not going to do that. But also, this is where we would want to be careful. If they did ask for the maximum revenue, we would have to do that. But they just asked for what price should they charge to maximize revenue, so we're fine. Questions, concerns on that? So again, here we had to use our number line because essentially one of the endpoints of our interval that we're looking over was infinity. So. Well, we've only got 3 minutes and you don't have any more notes up anyway to look at. So we're just gonna end there. We'll start chapter 5 on Wednesday. Your quiz, let me type it out in chat. We'll be on this 4.3, 4.4 stuff, but it will be about global max min. And I'm gonna say with one function. What I mean by that is, so today we went over, so sorry. What do I mean by global max min with one function? I mean something like this. Well, maybe not like this, but like the last part of this where you had to maximize revenue, or like this one where we had to maximize profit. I don't mean one like these first two that we did where you have two functions and you have to kind of manipulate the one to rewrite the other one. So your quiz will be more like maybe something like what we did on Friday, where I just give you an equation, ask you to find global max and mins. So your quiz will be on global maxes and mins, but it won't include things like 6 and 7, where you had to use two equations. It'll just be based off of one equation that you have to maximize or minimize. But it can be kind of any of those three cases. It could be on a closed interval, an open interval, or one where you have to consider the number line. But anyway, so that's that. Again, we're just going to finish 2 minutes early. If you have questions, feel free to stick around. Otherwise, I'll see you on Wednesday. I'll stop recording.